CPE 233. This is the introduction to experiment 1, and we're not doing the entire experiment. There's multiple parts to it. We're just doing part D, so keep that in mind when you read through it, because there are 3 other parts. So this is part D. It's a prime number generator. So what I want is to take a RAM and populate it with 16 prime numbers. So the 16 prime numbers, not all the prime numbers, it's every other prime number starting with 2. So it's going to go 2, 5, 2, skip 3, 5, skip 7, 11, skip 13, etc. So fill those up, fill up the RAM with those numbers, and then once the RAM is filled, I want you to continually show that sequence on the 7-segment display. So one at a time, you're going to step through and show the every other prime number one at a time on the 7-segment display. So there are some constraints for this experiment. You got to see the experiment for more details. So number 1, use only standard digital modules. Don't make up magic modules that do everything all at once. It's not permitted. I'll kick it out. Don't do that. Essentially, there is a prime number check module in there. You need to use that in your experiment, and you need to use it to find out whether a number is prime or not. Certainly more details about that in the experiment. Essentially, in your project, I don't want to see any mathematical operators except in RCAs or counters. So once again, this is kind of no magic circuits here. So this is going to need a state machine to control this and make it work right. And so I don't want any more than 10 states in your state machine. Should be doable. 4 or 5 states, not a big deal. And then I want the state machine to be 100% independent of the RAM size, which is essentially the sequence length. And what else? And I want the state variables to be the only memory in your state machine. So I don't want counters inside your state machine, or once again, magic numbers and weird stuff that in your state machine. Don't do it. So Canvas has a whole ton of resources on Verilog. There's muxes, registers, counters, anything else you can imagine. There's also a memory module, which is for an I'll say N by M RAM. Use that also. Anytime I need a state machine, I never start from scratch. I go find that cheat sheet for the state machine, drop that in my experiment, and then modify it as I need to. I don't start from scratch. I use what I'm used to. I use what I'm always using. If you use that, I can help you. If you don't use my approach for state machines, I'm going to have a lot of trouble helping you. There's also a universal 7-segment display module in there. Everything I know about that module is written in the header of that module. So check out the header of that module. It's high-level stuff. You don't need to know how the module works. You just need to know how to interface with it, which is once again written in the header of the module. And there's also the prime number check module. Essentially, you just give it a number, tell it to go, and it tells you if the number is prime or not. So the basic approach to hardware design is we're kind of taking a top-down approach. Is number 1, understand the entire problem. And once you understand that problem, you can start selecting digital modules for that circuit. Now, my contention is there's just not that many digital modules out there, and those modules don't do much, but you can do anything by making circuits out of those modules. So use those modules. Don't try to make a magic circuit by changing Verilog into a programming language, because it's not. Use the modules, interface with the modules, and then drop them down, connect them in your circuit. Next thing you need to do is control that circuit with a state machine. Generally speaking, always start the state diagram, then translate that state diagram to Verilog. And lastly, just implement your experiment in hardware, which for us is FPGA and your friendly Vivado. So the high level approach on this thing is to understand the problem, and then once you start understanding the problem, start designing it on paper. And the idea here is to keep it as clever as possible. Keep it as simple as possible. Don't be clever. Clever is hard to debug, and it doesn't work that well. We're not we're not trying to make this fantastic the first time through. And keep in mind, it is an iterative process. Design is iterative. You're not going to come up with an amazing working design the first time through. Start working with it on paper. As you work with it on paper, you'll learn new stuff, get new ideas, simply new ideas to simplify it, and you'll be done a lot quicker. My motto is always make it work and then make it work good. And so this class is make it work. So once it works, it's generally fine if you follow all the rules, but certainly your designs can be more efficient or better or whatever, but we don't really have time to go there in this class. So once you get a design, model your design with Verilog, including a state machine, and then test it on the board. Now, using the simulator is up to you, but you know, it's no one can get away without using the simulator. You got to use the simulator. Hopefully, your 133 teacher taught you all about the simulator. And whatever you do, always feel free to ask me questions, and particularly send me diagrams, circuit diagrams, state diagrams, whatever you think may help me help you. So lots of modules for experiment 1. They're provided. Don't write new modules unless you have a really strong desire to. Most importantly, most of the modules I provide are kind of templates. They're parameterized, and you need to instantiate those and override the parameter. If you change the template itself, I will not be happy. You need to use those templates, not change them, and just essentially override the default values. So when you're making this circuit, every input needs to be assigned, but you can leave the unused outputs just hanging. They don't need to be connected to anything. So do not remove unused inputs and outputs from your design. Inputs have to be assigned. Do not remove outputs from your design, from the template or anything, particularly from the instantiation. Do not remove them. Universal 7-segment driver is online, is on Canvas. Once again, everything I know about it's written in the header, as well as the prime number checker. Read the manual, read the header. Everything I know about it's in there. There's a nice timing diagram in the lab manual. Check that out. Anytime I need to use a state machine, I start with the template. By all means, you should do the same. If you don't start with that template, I have trouble helping you because I have one way of understanding state machines, which I understand really well, and any other way I have trouble with. A million different ways to model state machines in Verilog. Please use the way I use, and then I can help you. So once again, simulator is not necessary, but you're probably going to use it. So the important thing here is this experiment is going to need a clock divider. There's a couple clock dividers on Canvas. You're going to use the one that says testing in the name, and that way it makes your whole design easy to test. Real quick. Like the issue here is when you use a clock divider with the simulator, it's going to be completely wanky, and so what you want to do is not use a clock divider for the simulator. So the Universal 7-segment driver does have a clock divider, and so you're never going to see an output from the Universal 7-segment driver. What you'll be looking at in this experiment is kind of what's coming out of the output from the RAM mostly, or whatever part you need to look at. So you will most likely be using the simulator on this one. If you ask me questions, one of the things I'm going to ask you is, did you simulate it, or let me see your simulation. So these are the top level diagrams for this experiment. Generally speaking, when you press the button, it's going to start the sequence. It's going to go find all your prime numbers and then come back and display them. So this is the top level. It has a clock, it has a button to start the sequence, and these are the outputs on this thing. Now, I included LEDs on here so that you could maybe output a count, but that's up to you, and 4 may not be the right value on that one. I guess it is actually, but so you don't really need LEDs, but it will help you debug it if that's the path you want to take. So this is the prime number check module. It has a start button, which means go check to see if this number input is prime or not, and If you're in the test mode, certainly you can tie this to a 1. If you're running an open loop on the board, tie it to 0. More details done in the experiment. So once I start this prime number checker, it's gonna clear this done signal, and when that done signal is cleared, it's going to actually go back to a 1 when it determines whether this given number input is prime or not. So the issue here is when the done signal turns on, if the prime signal is on, then it's a prime number. If the done signal turns on, the prime number is off, then it's not a prime number, and you can use that in your state machine. So my suggested approach is to have it find all the prime numbers, not skip every other one, and then modify your state diagram to skip every other prime number. So the due date for this is 6 class meetings from the day it's assigned. And the issue here is I've always had problems with due dates. I think due dates kind of present a lack of flexibility in the course, but it's been problematic in the past, so I'm going to enforce due dates, unfortunately. Now, just keep in mind that in week 10 of last quarter, I was getting experiment 1s turned in, and I don't want that to happen. It's 6 class meetings, which is roughly 2 weeks. Get started early. Typically, when the due dates come up, I become very popular, which is the problem with the due dates. Okay, so when I have a whole bunch of people who put off working on the experiment, asking me questions, I have trouble getting help to those people, and I'm trying to avoid that. So put the time into this course up front initially. Don't fall behind. Feel free to send me your preliminary work, preliminary diagrams, ask me questions, anything you want. Just allow me to help you. But once again, due dates are back, and I almost feel like apologizing for the lack of flexibility, but it was something that was abused last quarter, and I want to avoid. So good luck. Ask questions.